Hey everyone, we're going to introduce you to our next unit, which is on momentum. Momentum is given the symbol P, mainly at this point because M was already taken for mass. We're going to use the symbol P. Momentum is known as inertia in motion. I want you to think about what that means, right? The two ideas that we're talking about. First, when we talk about inertia, and second, when we talk about motion, right? When we deal with inertia, if you remember, inertia is a property of all objects that have mass. And the amount of inertia an object had was based on the amount of mass that it has. When we deal with calculating momentum, it's going to be based on the amount of inertia. And then if we talk about the measurement of motion, we're talking about the velocity. So momentum is actually calculated by doing mass times velocity. And if you recall, velocity is a vector, meaning direction matters. Because velocity is a vector, momentum is also a vector. Now this is actually going to be really important, keeping in mind that direction is going to matter when it comes to momentum. When we're dealing with the direction of momentum, it strictly comes from the velocity. Whatever direction the object is moving in is the direction of the momentum. So if an object is moving to the right, its momentum is pointing to the right. Regardless of whether the object is speeding up, whether the object is slowing down, the direction of the momentum will come strictly from the direction of motion. Now, just like we've done in the past with so many different quantities that we've talked about, it's not usually enough to just talk about the quantity itself. We talk about how it changes. Right, so one of the things that we want to introduce is this idea of a change in momentum, which is just going to come from momentum final minus momentum initial. Right, anytime we're dealing with the change in anything, it's going to be the final minus initial. Now, there's a couple of different things that we want to point out when we're dealing with change in momentum. Basically, that one, the sign is going to matter. Right? If I am going to change my momentum in the direction I'm already moving, if I'm going to gain momentum, my object is going to speed up. If I'm going to lose momentum, that means it's because my object is slowing down. Now, the other thing that we want to think about is the fact that with direction mattering, or making a difference in what we're talking about, right? An object that changes direction is going to have an incredibly large change in momentum. And let me give you an idea of what we mean. I want you to imagine that we have two objects, one being a clay ball and one being a rubber ball, right? And both of them have the same mass of, say, 2 kilograms and are traveling towards a wall. right? Both objects have a mass of 2 kilograms, and let's just say both of them are traveling at a speed of 5 meters per second. That tells me that the initial momentum of each object would be 10. Well, 10 what? Since momentum is equal to mass times velocity, and mass is measured in kilograms, and velocity is measured in meters per second, our unit for momentum is just a kilogram meter per second. Now, the clay ball, when it goes flying at the wall, it's going to hit and stick, right? So its new velocity is going to be 0, which means it has a final velocity of 0 kilograms meters per second. The rubber ball, however, is going to do what a rubber ball does, and it is going to bounce back. And let's say that it again has a speed of 5 meters per second. That means it now has a final momentum of again 10 kilograms meters per second. However, with thinking of the fact that direction matters, it is now moving to the left, which means it's going to have a momentum of negative 10 meters per second, or kilogram meters per second, excuse me. That's incredibly important. If we look at the momentum, or the change in the momentum of the two objects, delta P is equal to PF minus PI. That is a 0 minus 10 for a delta P of negative 10 kilograms meters per second. But now think about the rubber ball. Delta P is equal to PF minus PI. My final momentum is negative 10 kilograms meters per second minus my initial 10 kilograms meters per second, which gives me a delta P of negative 10 minus 10 is negative 20 kilograms meters per second. We get a larger change in momentum when we hit and bounce off. This is known as a rebound. We get a larger change in momentum for a rebound than we do a stoppage. It takes more, it's a larger change in momentum to get an object to change directions than it does to stop it. And that's because of the change in direction, meaning a change in sign. I'm going to slide down to the next page here. The other thing to keep in mind when it comes to momentum, right? Just kind of going back to the very beginning, I should say anyways. When it comes to momentum, it's not now just about the mass of an object, right? When we just dealt with inertia, inertia was simply about mass, right? So, a not moving car would have more inertia than a moving person, right? We would have that, the only thing that mattered when it came to inertia was mass. Now, because of the fact that an object's mass and its motion are going to come into play, both of my variables are going to matter when it comes to determining an object's momentum. Let me give you an example of this. If I have a 7 kilogram bowling ball moving at 3 meters per second. That's going to have the same momentum. Let me rewrite that for you, sorry. As a 0.5 kilogram baseball moving at 42 meters per second. If I do my P equals mv for both of my objects, for my first object, I get 7 kilograms times 3 meters per second for 21 kilograms meters per second. If I do my P equals mv for the baseball, I get a 0.5 kilograms times 42 meters per second, which once again is 21 kilograms meters per second. Which means there are different ways that I can have an object with a large momentum. It can either be that it is moving very fast, or it could be that it is very large. Either way will give me a large momentum.